Previously, in the RH Saga, we alluded to this fundamental idea of F1 geometry many times. But what is the idea of F1 really, and what does it even mean to search for new geometry? To make sense of this, we need to talk about the Weil conjectures. The word zeta function can refer to many different things in mathematics, but the two meanings that are relevant for us are global zeta functions and local zeta functions. The global zeta functions are sometimes called L functions. This confusion around terminology, L function, zeta function, is not important. What matters is the conceptual distinction between the global ones that encode information from all primes and the local ones that relate to a single prime. Now, from numerical experiments, it looks like both kinds of zeta functions satisfy the Riemann hypothesis. This was discovered in the global case already in the 19th century, at least for the Riemann zeta function, and I believe also for Dirichlet L functions. In the local case, the Riemann hypothesis was discovered gradually from around 1920, beginning with the PhD thesis of Emil Artin. To make a long story short, after Artin's thesis, the Riemann hypothesis was proven for many special cases of local zeta functions over the following decades. And finally, it was proven for all local zeta functions by Deligne in 1974. And this amazing theorem, which gave Deligne the Fields Medal, is sometimes called local RH, or RH in characteristic P. This local RH is one of the 4 Weil conjectures, and we will come back to all of them. So, since the 70s, the situation is that we cannot prove RH for even a single global example, but we have a proof for all local examples. And this local proof uses geometry over finite fields, specifically tools like schemes, cohomology, and geometric families. Most of this geometry was invented by Grothendieck, who also got a Fields Medal for that. Here, a geometric family means that your geometric object can change or vary sort of continuously, although the word continuously has to be made precise for this to make sense. Everything so far is well known and completely uncontroversial. What's unclear, and perhaps also a bit controversial, is the idea that there might be another undiscovered geometry in the global setting that could play a role similar to schemes and cohomology, and maybe lead all the way to a proof of the global Riemann hypothesis. Okay, what is a local zeta function? And what does it mean that it satisfies the Riemann hypothesis? The easiest explanation is that an L function has an Euler product, as we have seen, a product over all primes. A local zeta function is just a single Euler factor in that Euler product. Let's go back to the LMFDB and find an example. And let's prove the Riemann hypothesis for at least one local zeta function. We could take an elliptic curve, genus 1, but let's go to genus 2 curves instead. List them by conductor and just take the first curve of conductor 169. You see the equation here. You can choose to homogenize it. But now go to the L function in the right-hand menu. And then scroll down to the Euler factors. Let's pick a good prime. I'll take p equals 5. The polynomial in this Euler factor is 1 minus 7t squared plus p squared, that means 5 squared, times t to the 4th. The zeta function is 1 minus 7t squared plus 25t to the 4th. Recall that p equals 5, and recall from earlier that t is just a code for p to the minus s. We can write the complex number s as x plus iy, and the aim is to prove that the real part of s, that is x, is equal to 1/2. To find the roots, set the zeta function equal to 0. That's 1 minus 7t squared plus 25t squared squared again equals 0. The quadratic formula gives a equals 25, b is minus 7, and c is 1. T squared, which is the unknown here, is then minus b plus minus square root of b squared minus 4ac, all that over 2a. This is 7 plus minus, let's see, square root of 49 minus 100. All that over 50. So t squared equals 7 plus minus I times square root of 51 over 50. Note that t squared is p to the minus s squared. That's 5 to the minus 2s, or 25 to the minus s. This is 25 to the minus x minus iy, which factors as 25 to the minus x times 25 to the minus iy. And this second factor has absolute value 1. It has exponent I, so it's on the unit circle. This first factor is real and positive. Now, back to the equation. Take absolute values of both sides. Left-hand side, it becomes 25 to the minus x times 1, which doesn't matter. The right-hand side, we use Pythagoras, keep the 50 downstairs. Upstairs, it's 7 squared plus 51, and a square root. Now we have 5 to the minus 2x equals, let's see, square root of 49 plus 51, that's very pleasant. That's 10 over 50. 10 over 50, that's 1/5, so 5 inverse. Very good. Same base. So 2x equals 1, and x equals 1/2. We have proved the Riemann hypothesis for this specific local zeta function. And I find this very satisfying. For completeness, I should add a few details. First of all, I lied to you. The actual local zeta function of this curve is the polynomial divided by 1 minus t and 1 minus 5t. The LMFDB displays only the complicated factor upstairs. The ones downstairs are always the same for every curve. For a higher dimensional variety, like a surface, there would be even more factors, both in the numerator and in the denominator. But all this does not affect the proof at all. You would anyway treat each factor separately and verify the Riemann hypothesis for each of them. Another minor comment is that for the polynomial, we did get real part of s equals 1/2. For this factor, you get real part of s equals 0, and here you get real part of s equals 1. In general, these would always be integers or half integers, and we say that the factors have different weight. In order to dive deeper into these local zeta functions, we need to say something about finite fields. A field is a number system where you can add, subtract, multiply, and divide. It is a theorem that for every prime power q, there exists a finite field fq with q elements. So, for example, there is a finite field with 5 elements. That's just 0, 1, 2, 3, 4, and everything is computed mod 5. There is also a finite field with 4 elements. That's 2 to the power 2. We can write the elements as 0, 1, alpha, and 1 plus alpha. All computations are done mod 2. So, for example, alpha plus alpha equals 0. And there's an extra rule that alpha squared is just alpha plus 1. A bit like I squared is minus 1 in complex numbers. Any finite field can be written down explicitly like this. And you can use Sage to construct this field for any given prime power. If you have a polynomial equation, say that genus 2 curve we just saw, then you can count the number of solutions in a given finite field. For a prime number, that's just counting solutions mod p. We did that a long time ago for an elliptic curve. For a higher prime power, it's similar. There is a finite number of possibilities for x and a finite number of possibilities for y. You can try all of them and count how many solutions there are. You can do this by hand, for sure, but it is easier in Sage. In Sage, we find these solution counts for the finite fields f5, f25, f125, and so on. And the solution counts happen to be 6, 12, 126, 628, and so on. And now, we can give the real explanation of what a local zeta function is. The local zeta function z of t for our specific curve and for the prime number 5 is defined by the property that the logarithmic derivative is equal to the power series of point counts, like this. Feel free to pause the video and just think about the logarithmic derivative. It is the derivative of log of zeta, and by the chain rule, this is also z derivative over z. The procedure of writing down z of t from the point counts is now just a page or two of very explicit algebra. I will not do the full computation here, but let's do half. I claimed that the zeta function was 1 minus 7t squared plus 25t to the fourth over 1 minus t and 1 minus 5t. Now, log of that is log of that polynomial minus log of 1 minus t minus log of 1 minus 5t. The derivative of that is, by the chain rule, polynomial downstairs and its derivative upstairs. Same here. The derivative is minus 1 and that works out in the end to plus. And same here, we get 5 over 1 minus 5t. The last two are geometric series, so 1 plus t squared and so on, plus 5 plus 25t plus 125t squared and so on. The first one is similar. It's minus 14t plus 100t cubed. All of that times 1 plus 7t squared and some higher terms that we could work out by a linear recursion, but we don't need that now. Now, the constant term becomes 1 plus 5 plus nothing more. That is 6. And the linear term becomes t plus 25t and minus this product 14t. So that is 12t. And then there are higher terms, but you already see that this looks indeed like the power series of point counts. So we did have the right zeta function. Now you can in principle work out the zeta function of any curve at any prime for yourself. Get the point counts from Sage and then find the unique rational function matching those point counts through the log derivative. Strictly speaking, you actually need just one more piece of information to do this. You need to know in advance what degree this polynomial, this numerator, will have. And this will be given to us by the Weil conjectures. Look at the zeta function again. Point number 1, this is a rational function, a polynomial divided by a polynomial. And that is not a priori obvious at all from the point counts. In fact, this is the first Weil conjecture, that a local zeta is always rational. Point 2, if you compute z of 1 over 5t, just plug in 1 over 5t for t and simplify, you will see that you end up with 1 over 5 times t to the minus 2 times the original z of t. This is the functional equation for the local zeta function. And it is Weil conjecture number 2 that such a symmetry always holds. Point 3, the real parts of the roots s are 0 and 1/2 and 1. When we substitute 5 to the minus s for the variable t. This is the local Riemann hypothesis, and it is the third Weil conjecture. Finally, point 4. The degrees of these polynomials are 1, 4, and 1. Recall that this was a genus 2 curve. So the complex solutions would look like this, a double torus, and the general statement for curves is that this middle number is always twice the genus. And this is the fourth of the Weil conjectures. What Grothendieck and his school did in the 60s was to invent an entirely new geometry, where these four statements could be proven. Not for isolated examples, that's quite easy, but for general classes of local zeta functions, and in the end, all of them. In this Grothendieck language, an equation is thought of as a scheme. What this means exactly is famously difficult to learn. But one possible reference would be these online lecture notes by Yuri Manin. You can associate certain vector spaces to a scheme. For a curve, there are three vector spaces called H0, H1, and H2. In our example, the dimensions of these spaces are 1, 4, and 1. It is hard to draw a four-dimensional. Each vector space comes with a linear map to itself. Think of it as a matrix. Here a 1 by 1 matrix, here a 4 by 4, and a 1 by 1, with some numbers in them. Finally, each polynomial in the zeta function will be the characteristic polynomial of that matrix. The vector spaces are called cohomology groups, and the matrices are called Frobenius. Using all of this machinery and these Frobenius matrices, together with lots and lots of deep and hard work, Grothendieck and Deligne, with some help, managed to prove all four of the Weil conjectures. Amazing. One final remark on the geometry of schemes. We could write down an equation like this: y squared equals x times x minus 1 times x minus t, where t is some parameter. When we vary the parameter t, we get different elliptic curves. And this is what I mean by a geometric family. It feels like a continuously parametrized family. But it's not, literally speaking, continuous, because t is not a real number, but an element of a finite field. So, what's the deal with F1, or the field with one element? First of all, the field with one element is just an expression. It's not a mathematically well-defined object. A field is an algebraic structure where you can add, subtract, multiply, and divide. And any field must have a zero element, identity for addition, and a one element, identity for multiplication. So that's already at least two elements in any field. What we mean by geometry over F1 is just a name for a possible future theory, like the theory of schemes, that could perhaps lead to a proof of the Riemann hypothesis in the global setting. The reason for this nonsensical word F1 is that if you compare patterns in local zeta functions with patterns in global zeta functions, then in many places where in the local case there is a prime number, in the global case it looks like there should be a number 1. So by analogy, in the local case, the zeta function comes from geometry over a field with, say, 5 elements. It looks like the global case should come from a field with one element, even if that makes no sense. Let's take one example where this happens. In the local case, there is a functional equation. For our specific curve, it was z of 1 over 5t equals 1/5 times t to the minus 2 times z of t. In the global case, there is also a functional equation, and if we use the theta function from the previous episode, the functional equation was theta of 1 over t equals plus minus some power of t times the original theta of t. And if you look at these two functional equations, they are precisely of the same form, provided only we could exchange the number 5 for the number 1. Maybe this is just a coincidence or a superficial similarity, but when there are many similarities like this, you start to suspect that there is, or there might be, some deeper analogy and some deeper links, and maybe a new geometry on the global side. There is a lot of intuition around how this might work. For example, some experts believe that instead of the finite fields appearing in the local case, we should have roots of unity in the global case. We had local f5, f25, f125, and so the powers of 5. The roots of unity, if we draw them as complex numbers, would be the first roots of unity, second roots of unity, third roots of unity, and so on. Another intuition is that the basic geometric object in F1 geometry should be like a line, where all the prime numbers are points, and then there should be one extra point at infinity. And somehow, an Euler factor from a given prime number should come from that prime number point, and the gamma factors in the completed L function should come from the point at infinity, or the infinite prime. But all of this is intuition and analogy. We are reaching in the dark for something that might not even exist. Or maybe it does exist, but some of our intuitions or ways of thinking about it are just wrong. Who knows? To my mind, this is the greatest mystery in all of math. Can you read about F1? Well, there is a pretty long list of proposals that people have made as to what F1 geometry might or should mean. In these papers, there are lots and lots of promising ideas, creative ideas, and I certainly don't understand all of them in detail. However, to the best of my current understanding, these proposals haven't really led to significant new theorems for L functions, not even for the Riemann zeta function. There may be other applications, but so far not for the original dreams around RH and related number theory problems. Still, it is very interesting to read about these proposals. And here I will end by pointing to some of the best and most interesting references. There is one paper called Mapping F1 Land, which gives some general background and an overview over the proposals that had been made at the time, back in 2009. For some of the deeper motivation and the dreams that many people had, An even better source is the PDF put together by Leven called Geometry and the Absolute Point. I guess this is a picture of an ordinary finite field on the left and the field with one element on the right. Here you will find more of the intuition expressed by people like Manin, and maybe most importantly, André Weil himself, who discovered the Weil conjectures for local zeta functions and also spent many decades thinking deeply about the global Riemann hypothesis. Then there are also various more recent things on the archive. For example, this new paper called On the Metaphysics of F1 by Alain Kohn and Katerina Consani, a paper dedicated to the memory of the immortal Yuri Manin.